Rate-based multiplexers are advantageous in the sense that once rate matching has been done for all the sources of heterogeneous data rates, then they can all be carried in a very safe and premeditated manner between the multiplexer to the demultiplexer. It is not the case when we start looking at non-rate based multiplexers. The kind of increase in complexity arises as we shall see. In this module, we shall understand how non-rate based multiplexers differ from rate based multiplexers and how non-rate based multiplexers necessitate multi-constraint feasibility, because we just understood finding feasible routes using multiplexer kind of rate based matching is relatively a simple problem, but we'll see how non-rate based multiplexers complicate the problem. Non-rate based multiplexers, as discussed in Anurag Kumar, are akin to statistical multiplexing techniques in which there is a factor called probability that emerges. Because of this probabilistic behavior of non-rate based multiplexers, the situation or the requirement on determining the behavior of the individual path matrix becomes very important. Non-rate based multiplexers are unlike rate based multiplexers because the rate matching requirement is now relieved. But when this is relieved, certain other requirements pop up. For example, bit error rate would now emerge because of transmission errors, rate mismatching problem. The packets would also now be lost. So when the packets are lost, then packet retransmission mechanisms need to be incorporated. And then some flows would still require that preferential treatment is given to them. So unlike rate-based multiplexers in which we could only address this problem by simply increasing their weight, as in weighted fair queuing, here it is not that simple. So when we talk about non-rate based multiplexers, we say it is a multi-constrained feasibility problem. Now we have, in addition to the primary constraints laid out by the routing problem, that is route and rate, we have additional constraints, and the objective function would now be to respect all these constraints and still find a feasible path. What if there are multiple paths which satisfy all m constraints? It's a very good but unlikely situation. What if it still happens? If it happens, then it's obvious that all m constraints are being satisfied. So there's no additional criterion that identifies a mechanism to choose one path from the other, since all the paths are satisfying the m constraints. In that case, taking any path would still fulfill all the m constraints, and that is what is generally adopted. Let's look at two-dimensional representation of a heuristic. We look at a constrained region in which we have lambda 1 of a path and lambda 2 of a path are individual path matrix. Now lambda 1 and lambda 2 are just two of the various path matrix. Since the conjoined, or in other words, the resultant effect of combining all these path matrix is eventually important. So for the sake of convenience, we look at the interplay of two routing path matrix. We see that these lines with a slope minus alpha 2 divided by alpha 1 represent these concentric lines. The outermost line is the least constraint and the innermost line is the most constraint. And the requirement given by the network users is represented by the dotted rectangle. If different paths exist which satisfy these m constraints, we would take the constraint path that is within the bounds of the dotted rectangle. Using this is a very good way to understand the relationship between various routing matrix working together to form the resultant routing matrix.